I've been looking after the meteorite collection now for quite a number of years. I'm loath to call myself an expert because in a way I haven't actually been to train as a meteoricist. But I think experience and knowledge that I've managed to glean has given me quite a good insight into meteorites, what they are, where they occur, especially in a Scottish sense. And hopefully at the end, if there's any questions, I will be able to answer them at least without looking up things on Google when I'm doing it. So I'm going to start by putting up this slide, which I always kind of use when I'm doing a meteorite talk, which is what are meteorites? Because there is a kind of confusion a little bit about the word meteorite and what it is and what it represents and what are the actual meteorites that we have collected in the museum and many other people collect. And these three definitions appear in different on different sites on the web. The top one is from the Oxford English Dictionary, which in my view is completely useless and has no relevance, I think, to this discussion. But the other two are possibly more relevant, more truthful, if you want to call them that. And the last two particularly, well, I'm going to speak about this in a second, put the emphasis on that the object has hit the ground and has survived that impact. And in both of these, they talk about surviving the impact. But in fact, that's not always the case, as I'm going to show you. But yes, they are. I think the thing to remember is that they are natural objects. They're not man-made objects, so space debris does not qualify as meteorites, even though they are seen to fall and they do cause a fireball. I think one recently over central Scotland was thought initially to be space debris, but turned out to be an actual meteor. This was meteorite when it eventually hit the ground, but it didn't fall to Earth in Scotland, which is a pity because we could do with one more. Yeah, two of the biggest meteorite strikes in history, I mean, this is not just human history, but all history, were the Chicxulub, which is in the northern part of the Yucatan Peninsula in Mexico, and the one on the right shows you the Ries crater in Bavaria in Germany. And in each of these cases, the meteor, or you can see from the scale that the Ries crater in Germany is at least 25 kilometers across. And in the Yucatan, the diameter is about 180 kilometers. That's from one side of the circle to the other. They did not survive the impact. And then neither did the dinosaurs, especially the Yucatan one. There is no real material from the Chicxulub meteorite. There is obviously material that was thrown into the atmosphere by the impact, which caused a great global cooling, which is thought to have been germane in the end of the dinosaurs. And certainly we find increased iridium qualities in the level that goes between the level of sediment that forms the boundary between the tertiary and the Cretaceous, which is what is often the marker point for the end of the dinosaurs. The Ries one was smaller and much smaller. It didn't really cause the extinction of any mass extinction of species. In both these cases, no material survives from the actual impactor, but there are many impact structures that do survive, and that's how we know that they're meteorite strikes, because of the nature of the rocks or the nature of the interaction between the meteor and rocks, which has been quite widely studied. Incidentally, the Chicxulub body, the original body, was thought to have been around about 1 times 10 to the 15 kilograms, so quite a sizable body, which hit. The Ries one was much much smaller. Now, there's again back to this idea that there might be a bit of confusion about meteorites and meteors, and there's a lot of names which sometimes appear in the media connected with this phenomena. Asteroids, obviously, is probably something people are generally aware of. They're large, well, small to very large bodies which orbit the sun in a belt between Jupiter and Mars. They are probably the main source of the meteorites which land on Earth, and they can vary in size from dust to up to the largest one, which is Ceres, is just a tiny bit smaller than the moon, so they can be quite large objects. A meteoroid is simply the name we give to the body as it travels through space on its path. It's not interacted with anything, it's simply a large, what could potentially large object. Asteroids are often thought of as being very large, whereas meteoroids are kind of medium sized, perhaps. A comet, well, I think everybody has probably seen a comet at some point or other. Of course, it has its magnificent tail. These are objects which come from the furthest reaches of our solar system, from the so-called Oort cloud. And they are essentially, as one American astronomer called it, a dirty snowball. So they're basically rock and dust and other things held together by ice. And as it approaches the sun, the ice melts and you get this tail of debris, which forms always pointing away from the sun. So although it looks like the tail should be behind it, it's actually, it can be in front of it if it's going away from the sun. The tails of meteorites, tails of comets are also seen on Earth as meteor showers. So the meteor showers that we encounter quite regularly on Earth are in fact the Earth passing through the tail of a comet. A meteor is kind of like the next stage of sort of meteoroid. It's where we see it flashing through the sky. It can be a fireball or a bolide, which is an old name for that. Shooting stars are more like dust particles because they are almost instantaneously gone when you see them, and there's no way that they would fall to Earth. They're just simply, they don't have enough mass, they don't have enough momentum behind them to do that. Near Earth objects are kind of a new phenomenon. They're, as the name suggests, large objects that are close to the Earth. They might even be in our orbit or close to our orbit. And I think as our technology develops, we're beginning to see more and more of them. And obviously, it's a worry if they're very large, because if the Earth, it could spell big trouble. But we're now more aware of them than we were several years ago. The last one might be a bit odd, Trojans and Greeks. These are actually names which are given to belts of asteroids which follow planets. So we can see in this rather stylized image, we can see that the main asteroid belt is there between Mars and Jupiter. But in the same orbit as Jupiter, we have two bodies of asteroids, the Trojans and the Greeks, and they were just given that name by astronomers. They started giving them the names of Greek heroes and Trojan heroes, and then it kind of became a bit of I wouldn't say a game, but it became the standard thing to do, was to name them after that. I think the Trojans actually come in front of the planet, the Greeks are in front of the planet, whereas the Trojans follow the planet. They actually, although you can't really see it from here, they actually are at a specific point in the orbit at 60 degrees from the planet, from the sun to the planet, the axis from that, and same on the other side. So it's called the Lagrange points, and these are the positions of these groups of asteroids. Incidentally, Earth does have a Greek, just one or two. Mars, you can just possibly make out on this diagram, has a couple as well. So they are just simply held by the orbit of the planets, by the gravitational force of that, and also the sun. So where do meteorites come from? Well, most, as it says in the top bullet point, come from the asteroid belt, which lies between Mars and Jupiter. The asteroid belt is not a static thing. It moves in orbit around the sun, much as the planets do. And as they do, they're influenced by the huge gravitational pull of Jupiter, which makes them move within the belt. So they're not on a fixed orbit, they actually can be moved back and forward. And of course, this causes collisions. And if a collision happens, the chances are some of it will be knocked out of orbit and head towards the center of the solar system. Also, there is some footage of an asteroid being knocked out and then hitting the surface of Jupiter as well. But that's probably rarer. The asteroid belt itself has about, as it says there, 96 to 100,000 individual objects, and these are the ones that have been numbered. So there's probably 10, maybe 15 times more which haven't been numbered, and these are still to be recorded. And also 12,000 of them actually have names as well. So as it says below, the Ceres is the largest asteroid. It's about 950 kilometers across, which is smaller than the moon, but not too much smaller than the moon. And the largest asteroids have also undergone a certain degree of differentiation, so they will have developed cores and mantles, much like a planet too. So they're very much, or were very much, an active geological body as well. The other thing about asteroids, is that in films like Star Wars, you often see ships coming out of hyperspace into an asteroid field, and it's like they're surrounded by countless numbers of asteroids. But in fact, if you stood on one asteroid, you probably would not see another one because they are so far apart, and they're also very, very dark. So chances of seeing them are quite small. How do they reach the Earth? Well, as we said, collisions within the belt cause the asteroids to bump into each other, and some of them are forced out of orbit, and they are sent towards the sun by the sun's gravitational pull. And if it passes close to a planet like Mars and Venus and Earth, the gravity of these planets can also pull them in to a certain degree, and where they will strike the ground and hopefully survive. And they can be collected and gathered in. The last phase, obviously, is it enters the Earth's atmosphere. You get this fireball forming, which is mainly caused by pressure of the object coming through Earth, kind of almost like compacting the air in front of it, causing it to heat up. And you get this fireball effect, which is really, really short, a few seconds really, and then it hits the ground. It also leads to these kind of myth that the meteorites are hot when they fall to Earth, when in fact they are generally not hot when they hit the Earth, but actually if they've been in deep space at almost absolute zero for such a long time, they are still going to be cold when they, even after entering the atmosphere. So they are likely to be at best ambient temperature, and at worst extremely cold. And there have been reports of frosts forming on meteorites when they come to Earth. Just a few facts and figures, I guess. The flux of meteorites, that's the number of meteorites that fall per annum that weigh over 100 grams, is between 100 and 120,000. Now these, as I say, can be anywhere from 100 grams upwards. And when you see the figure below, which says only 35,000 meteorites have actually been recovered and are in collections, then there is a bit of a disparity there, because we've been collecting and gathering meteorites for over 100 years. So it kind of leads to, well, what happened? Well, the rest of them probably fall in the sea. The sea is the largest part of the Earth's surface, the oceans, and that's probably where they mostly end up, or in areas where they can't be accessed quickly or easily. So yeah, and they don't survive on the Earth's surface for that long. They can depending on their composition, they can weather away quite quickly. And in some cases, most experts figure that a meteorite might last no more than 150 years on the surface of the Earth without being eroded away. They contain iron minerals, and these iron minerals will rust, and they eventually will cause it to break up and weather away. The speed at which they hit the ground, as I say, it can be about 500 kilometers an hour or 300 plus miles an hour, but the larger ones with more impetus and more momentum will hit the Earth at several thousand kilometers per hour, which is not something you want to be standing under when they hit. So as I said before, when they pass through the atmosphere, the outer surface, and I mean, when we say outer surface, I mean millimeters. We're talking about, 1 or 2 millimeters will melt, causing this phenomenon called a fusion crust, which is really black and shiny. And the rest of it will have not been heated up long enough to warm up, so that they will be still cold when they hit the ground. And that's probably quite a good thing, really. Now, the largest meteorite to fall to date that we know about, and as you can see has survived, is the Hoba meteorite from Namibia. It weighs approximately 60 tons to 70 tons. It's an iron meteorite, so it's solid iron from outside in. You can see gauge the size of it by these two people sitting on top of it. Its original weight was thought to be about 100 tons, and it surprisingly did not create a crater, even for something so large. It didn't create a crater when it landed, and the reason is it's probably to do with the shape. Shape is kind of flat, and we think that when it came in towards the Earth, it came in at rather a shallow angle and actually skipped like a stone on water across the outer atmosphere until momentum was taken away, and it actually landed on Earth at a much slower speed than was expected. It was found by accident. Somebody, you can't really see from here because they've built this nice little kind of viewing area around about it, but it was simply a farmer ploughing. The plough hit something large, metallic, and of course thought it was just a big rock, but eventually, of course, they dug it up and found it was more than just a big rock. It was a big meteorite. The largest total, this is the largest individual one, the largest total fall was the Campo de Cielo in Argentina, where certainly in excess of 100 tons of material fell, but there was several individual pieces that make up that over a fairly large area. And that fell within human time, so it was noted by local indigenous people as well, and they developed many stories and tales around that. Now, meteorite type. Now, you probably already know that there are several different types of meteorites. I've already mentioned iron meteorites, which you can see in the top right-hand corner there. But there's essentially 3 types of meteorite. There are stony meteorites, stony iron meteorites, and iron meteorites. But the stony meteorites themselves are subdivided into 2. There are the chondrites, which are the most common, and I'll show you a chart in a minute. They form about 85, almost 85% of all meteorite falls are chondrites. Acchondrites are much rarer. They're different because they don't contain the chondrules, which typify a chondrite. They're also much younger than the chondrites, which tend to be around about the same age as the solar system. They're left over from the formation of that. Acchondrites are often from planets. So if you have a meteorite which has hit Mars, then the object which gets thrown off the surface of Mars, it could come to Earth as an achondrite meteorite. Indeed, we do have Martian meteorites in our collection, and certainly on display. The iron meteorites are probably about the same as the achondrites in terms of their, in terms of their abundance. They're about 7 to 8% of all meteorites are iron found meteorites, and the stony iron are the rarest. There's only about 1% possibly of that. And while iron meteorites are thought to be core material, so if we were to go into the center of the Earth, the material that we find there, which is an iron nickel compound, is probably going to be similar to what an iron meteorite is. Stony Irons possibly represent a transition zone between the mantle and the iron core, and they contain both the iron and silicate material within it, and they can vary quite a bit as well between them. And these are, because they're so rare, they're probably the most valuable in terms of collecting. And here we can just see a very poor focused. Yeah, sorry, I should have got a better one. But you can see roughly where they lie. So 84% stony chondrites, 8% acchondrites, and the rest just making up the numbers, really. As I said before, there are two types of stony meteorite. There's the chondrite and the acchondrite. Chondrites contain chondrules. These are little spheres of glass and are essentially material that formed at the beginning of the solar system and were kind of coagulated together to form larger bodies, which became, well, when they fall to Earth, become the chondrites. I'll show you an image of that in a minute. Acchondrites, obviously, as the name says, a chondrite without chondrules. They're more like terrestrial rocks. They are much younger than chondrules. Some of them are less than 1 billion years old, which of course is still old, but not as old as the chondrites, which can be about 4.5 billion years old. In some cases, they're similar to terrestrial rocks in their composition because obviously they've been formed by geological processes on planets like Mars and the Moon, so they're not that different from what you find on the surface of the Earth. And this makes them probably more difficult to find. So it's possible that the acchondrites are underrepresented in finds because they're just too similar to Earth rocks. This is an image of a chondrule. It's obviously the round. There's actually several of them. The biggest ones are in the middle, running across in a line. But you can see that even the matrix is essentially made up of chondrules as well. They are glass, so they were formed at high temperature and cooled quickly, so they're not crystalline in that sense, but they are formed of material which you find on Earth. So they're not extraterrestrial in the sense that they're unusual or rare materials. They're actually pyroxenes and olivines in the same way that we find these particular minerals on Earth. The most interesting type of the chondrites possibly are the Carbonaceouschondrites. These are they are chondrites, as the name suggests, but they contain a high percentage of organic molecules and also water. And they are obviously black all the way through in terms of their color. They're not actually like other meteorites where it's paler on the inside. The dark fusion crust gives it that outer blackness. Carbonaceouschondrites tend to be really dark all the way through. They're the only meteorites that I say smell. And if you were ever to come to our collection and look at some of our Carbonaceouschondrites, you would note that there's a bit of an oily, organic-y kind of smell about them. And some of these organic molecules are postulated to have been instrumental in starting life on Earth because some of them are amino acids, some of these long chain carbohydrates hydrocarbons were, if in essence, something that was brought into Earth and may have triggered off the spread of life on Earth. Also found within Carbonaceouschondrites are diamonds, which are, as it's sure you know, nanometer-sized diamonds. And these are thought to have originated from outside our solar system. So it's possible that they were part of a supernova, and the material was then obviously scattered away, came into our solar system to the pre-solar disk and was incorporated into certain types of meteorites. And here's a Carbonaceouschondrite, the Murchison, nothing to do with the Scottish geologist called Murchison. It's actually a town in Australia called Murchison, which may have been named after Murchison, but I don't know. But you can see how the interior of it is extremely dark, which compares with the much paler material that you find in other meteorites. Acchondrites, again, are just stony meteorites that don't contain chondrules. They're much more similar to terrestrial rocks. Their textures and mineralogies are indicative of an igneous origin, and they include what I call the planetoid meteorites, that meteorites that originate on the surface of the Moon and Mars, excepting, of course, the Moon is not a planet, but hey. And this is a Euclide, and you can see here also how pale the interior of it is compared to the black crust. Euclide is actually a rock, not just the name of a meteorite, but it's also a rock that you find on Earth. It's a kind of gabbro, I think. It's certainly an old name that was used for this type of rock, terrestrial rock. Iron meteorites, composed entirely of iron, nickel, and iron in an alloy. They are thought to represent the metallic core of a small planet. They're obviously highly magnetic, which is where you find the idea that all meteorites are magnetic. Well, yeah and no. Some of them are less magnetic. But importantly, they were also a source of iron for some early human cultures, where it was the technology to smelt and recover iron was known, and the the iron was used. And although it's obviously iron isn't exactly an easy thing to work with, it can be cold work in some circumstances. And what we can see here is this is from the tomb of Tutankhamun. It was a knife found in the tomb. It was later analysed and found to be meteoric iron and nickel. And you can, well, I don't know, maybe with the eye of faith, I can sometimes say I can see the Bidman statin pattern, which I'll explain about in a minute. But again, iron, a readily available source of iron, was meteoric iron, and it was certainly used. Another interesting one with the story behind it are these harpoon tips from the Inuit tribes of Greenland and very north of Canada. When Commander Peary was exploring the area in the 1860s, he noticed that the local Inuits were using narwhal, which is the main part of this harpoon, is a narwhal tusk tipped with iron. Now, the Inuit didn't have natural sources of iron, and they were not therefore able to work iron to any degree at all. So they couldn't, buy in iron and smelt it. They just didn't have the technology. So when Peary found these, he asked where they were from, and eventually, reluctantly, I probably gather, one of the Inuits showed Captain Peary where they got the iron, and it was 4 giant iron meteorites that were found in Greenland at Cape York, which they were using for raw material, and they were literally hammering it with stones and antler to shape it and to chip bits off, and they were then able to use these tips to tip their harpoons. This particular specimen comes from the British Museum, and it again, when it was analysed, it was found to be meteoric iron. Incidentally, when Peary was leaving, he actually took the 4 iron meteorites with him to the US, where they are still on show in the Natural History Museum in New York, leaving the Inuit with, well, nothing really. So that was a bit of a shame. Finally, with iron meteorites, you have this patternation called the Bidman statin pattern. It's essentially these lines are crystal edges. As the material slowly cools, they form this pattern called the Bidman statin, and it's when the solution cools, it kind of it enriches and then depletes, and then enriches and depletes in nickel as they are taken out of solution, forming this pattern, which you can see here has been used quite nicely in a ring. They have attempted to try and recreate this in the laboratory, but they found that they couldn't, because in fact it requires long, slow cooling obviously in space to affect this kind of pattern in the metal. And although I think they did manage to create some in brass, they haven't been able to do it in iron. So if you see something like that, it's definitely extraterrestrial. Excuse me. Right. Finally, Stoney Irons, a mix of silicates and iron nickel, the rarest of all the meteorite groups, thought to represent the boundary between the core and the mantle. Some researchers now think that they represent a mixing together of core mantle when it wasn't quite solid, so that a large strike on the planetoid caused this kind of mixing between the mantle and the crust, and you get this kind of overlapping that occurs. Again, nobody was there at the time, so we can't really prove it for sure, but that's kind of the two main schools of thought. They're also thought to be probably the most beautiful, and you can see an example here. This is a slice of the iron meteorite, the Esquel from Argentina. It's 5 millimeters thick, and when the light shines through, you can see these olivine crystals glow rather nicely, and the metal parts, you can see the shiny metal, do show some Bidman patination as well. Now, to the crux of the matter, Scottish meteorites. Well, we're not well endowed with meteorites in terms of the UK. There have only been 23 confirmed falls or finds. Now, at this point, I'm going to explain the difference between a fall and a find. A fall is a meteorite that's been recovered after being observed. So if you see something come down and you recover it immediately or soon after, it's a fall. If you come across it serendipitously, you're just tramping through the highlands, luck would be a fine thing, and you come across it and you take it in and it's analysed and it's confirmed as a meteorite, that's a find. So it's kind of the difference between the two. One is observed, the other is not. There are only 4 Scottish or known Scottish meteorites. Now, I was talking to Emily beforehand and we were discussing the idea of micrometeorites. It's true, micrometeorites occur everywhere, but we can't really count them because there are so many, countless, thousands, even possibly millions of micrometeorites. Although it would bump up the figures a bit, it would probably not be really worth counting them as individual meteorites. So the 4 are High Postle, which is near Glasgow. In fact, it's in Glasgow now. Glenrothes in Fife, the Strathmore, which is the, you may know Strathmore from the mineral water, but it's the area that runs kind of from Perth towards the northeast. And the Perth itself was also the site of a meteorite fall. And the largest being the Strathmore, where 15 kilograms of material were covered in 4 pieces. The centenary of which was in 2017. And here's a map showing the sites of them. You probably notice from this map, which is not exactly, I suppose, the most accurate of maps, that all 4 Scottish meteorites fell in the Central Belt. And there's probably a number of real logical reasons for that. One being the Central Belt is where most of Scotland's population live. So the chances of seeing or observing something that's going to fall is probably higher in the Central Belt than it is in the more remote and less well-populated areas. And that's probably why the 4 that we have are all from the Central Belt. The 4 that we have are all actually very similar to each other. They're not by any means from the same body, but they are very similar to each other in type. And they fell probably within about 100 years of each other. So again, not a long time between them, but at the moment, that's all we have. So if anyone's out there looking to collect them, please do and add to our total. We're due another one, I'm pretty sure. We'll start with the High Postle. The High Postle is the oldest in the sense that it was the oldest terrestrial meteorite that we have. So it fell in 1804 at High Postle village or farm, which at that time was outside the boundary of Glasgow. It was kind of in the countryside. north of Glasgow, and it was observed, so it is a fall by quarrymen in the quarry that it fell into, and it was recovered by the quarrymen, if you like, and the boss of the quarry got hold of them and sent them off to the museum in Glasgow, the Hunterian Museum, to be examined. Two pieces were originally recovered, but the larger of the two at some point was lost. And we're not sure how it was lost. It was just, pieces go missing, I guess, all the time. So the smaller the piece is the only remaining piece. And some smaller fragments have come off the larger pieces. So we actually have one, but not from the one that's now in the Hunterian Museum in Glasgow, probably much to their relief. And this is I don't know if you can see this map very well. This is an actual photograph of the meteorite that's in the Hunterian Museum. You see how pale the internal portion of it is. You can see the brown marks, which represent rusting iron mineral, and of course the black fusion crust on the outside. The map is actually really poor. I apologize for that. The blue line running through it is the Forth and Clyde Canal. It was called the Great Canal in those days, and it had just been built. And by looking at old maps, you can see there's a number of quarries in the area that's marked out in pink. It's like a giant Venn diagram there. And these represent reported sightings that were in the newspaper. So one person thought it fell about 1.5 miles from the Kelvin Aqueduct. Another thought it was about 1/4 mile from High Postle Village, which would have been around about there. So by doing this and then trying to maybe give a rough idea where it might fall, we think it fell somewhere in that pink area. The next up is the Perth We Try. It was reported to have fallen on 17th of May 1830 in a thunderstorm. But the information about that is, as I say there, it's actually rather scant and possibly a bit vague. The only information that is available came from handwritten labels that accompanied the specimen that's now claimed to be the Perth meteorite. And it was written about in a scientific journal called the London and Edinburgh Philosophical Magazine. And that's kind of about it. There's no real other information. There's no newspaper reports that I can find that actually tells the story of it from a non-expert point of view. The area which it fell is on this photograph on the left. It's the large green area that is towards the bottom right-hand corner, where you can just clearly see there's a golf course there. The other green area on the other side of Old Perth is the South Inch. And of course, that led to the famous joke about Perth, how the smallest city in the world, because it only has 2 inches, the North Inch and the South Inch. So I can hear the roars of laughter on the screen here. But so it fell in that area. We're not entirely sure. The North Inch was also the scene of an infamous battle between 2 clans, where rather than have a rather disorganized battle with 2 sets of, they actually selected 30 men from each side who basically faced up to each other and fought each other to the death. And I thought, well, what people did for entertainment in those days, I just can't imagine. But this is the piece that's in the British Museum, and this is kind of about all the information that's available. It fell in 1830, but the paper written by Neville was presented in the paper by, as you can see, it's 1862, so 30 years after the event, it was actually brought into the public domain. So interestingly, the largest piece of that is not in the UK, but it's in the Museum of the Geological Survey of India. And this puzzled me for a long time. Why on earth would it have been moved to India or given to India? I think at the time when you look into it, you find that the head of mineralogy was William Story Maskelyne, and he was doing a lot of swapping around, and he was exchanging material with other museums. And we probably think that's when it actually ended up in India. Don't know for sure, but that's my theory. Now, the biggest of all, the Strathmore, which is one that we celebrated, the Centennial, fell on the 2nd of December 1917, around about 1 p.m, so in the middle of the day. It was widely seen across central Scotland and northern England. It was a clear day, it was cold, it was December obviously. And 4 fragments totaling about 13.4 kilograms were recovered at the time, and they were all recovered from a different site. So the sites, when you plot them on a map, although I don't have that map here, are all lined up with each other. So the meteorite arrived from the south east, travelled across the North Sea and then across the Lothians and the borders, across the Forth, across just a wee bit north of Edinburgh, and fell in the Strathmore, having exploded over the Sidlaw Hills into the 4 pieces that we found. But there probably are more pieces there, because if something like that explodes, there's probably likely to be lots of smaller pieces that were never ever recovered. Maybe they fell into a loch or a river or something like that. The most famous piece attached to this is the one that fell through the roof of a house. And here's the most famous photograph of it. You can see the hole. And I'm going to put, although I can't show you, the hole should be put in inverted commas there. When the meteorite was recovered, the family, who are the older couple living it, their young daughter Elizabeth went up in a ladder to look through the hole and saw that there was something there, but she couldn't quite reach it. And the next day, somebody came from either the estate or from nearby to repair the roof. Obviously, in December in Scotland, the last thing you want is a hole in your roof. And they repaired the roof, and he recovered the stone and gave it to the family. And but by this time, of course, news was getting out about the fall. People were coming, and you can see that the car parked in front of it is actually, when you blow up this image to a larger size, is actually a taxi from Perth. It's got a Perth taxi cab license on it. So we think that either Henry Coates, who was the curator of Perth Museum at the time, or a reporter from an Edinburgh newspaper came up on the train, hired a car or got a cab from Perth, went to photograph. Of course, the roof had been repaired. So he photographed the building as it was when he arrived, and then later added the hole by scratching away the enamel on the actual negative to create a hole, which we later looked at and found that it was probably too big for the size of the meteorite, and it would never form a jagged edge like that. It would be a fairly clean, maybe breaking a couple of slates, and that would be it. So this is an early example of photoshopping that can be kind of thought of as a way to, just enhance the story a bit. Newspapers, what did they say? Never let the truth get in the way of a good story. Finally, Glenrothes. This was a find, so not a fall. It was discovered in 1998 by a local meteorite collector and dealer who sent it away for analysis, and it was confirmed as a meteorite. There's no fall date with it, but studies of the weathering of meteorites and of this particular one seem to suggest that it might be about 150 years old. We haven't had the opportunity to look at newspaper reports to see if there's any mention of a kind of phenomenon which happened at the time. So we're not entirely sure if that's true. So maybe between 100 and 150 years old. It was the last one to be confirmed, although probably not the last one in age for Scotland. Again, I apologise for the map. It's not coming out quite as obvious as Glenrothes is at the bottom right-hand corner there. You can see it's the area called Leslie Parks in Old Town, and there are 2 lochs to the west, northwest of it, and it was found near the one marked with the pin, I think they call them, and it was in the fields round about that. So we're not entirely sure exactly where. It didn't fall in the loch, but which is what you might think from the picture. It fell into an area just around the side of the loch. Finally, meteorite-related material. Well, when a large body like a meteorite hits the Earth, it imparts, first of all, huge amounts of energy into the local geology. and this can lead to melting and shattering of local rocks. They can create massive dust clouds, which with the Chicxulub was massive enough and big enough to actually block the sun out and cool the earth down, thereby possibly putting an end to the dinosaurs. But melted rock fragments can also be thrown out of the crater, and as they cool and tumble, they form these kind of unusual shapes. These are often called tektites. They are essentially earth rock glass because they cool quickly, and they're quite sought after because some of them have a very, and I'll show you in the next slide, some of the unusual shapes that they form. Desert glass, which is the last item here, is formed when we think when a large meteorite approaches the Earth but explodes above the surface. So the heat is pushed down and it melts the surface of the desert and forms a kind of glass pan on the surface. The most famous one being the one that's in the area of Egypt and Libya on the border area. Very dangerous area, so don't go there. But we have material from the Libyan desert glass, which is a pale greenish yellow color, and it was used in the funeral jewelry of Tutankhamun as well. So it has connections way back to the early Egyptian cultures. And here are some of these tektites. Shows you how unusually shaped they are. These are, the one at the bottom right is what something called a dumbbell for obvious reasons. The one on the bottom left has that almost, you can almost imagine it being molten and pulled out into a little tail. The ones in the top left are the australite buttons. These are formed when they come to Earth, and almost like a shield forms from the molten glass, leaving a little blob in the middle. The dumbbell ones are caused by tumbling. So as the glass forms and tumbles, it kind of elongates and creates this kind of cigar shape. I would hesitate to call it anything else. The last picture on the top right is actually a piece of desert glass from Libya, and you can see the pale green color that is normally associated with a desert glass. Right, finally, craters. Obviously, the evidence for meteorites hitting the Earth are craters. If you look at the Moon or Mars, the surface of these planets are pockmarked with craters, big and small. Some of them are volcanic, but the vast majority are caused by bodies, meteorite bodies coming in and hitting the surface of it. There have been two massive periods of meteorite falls, the Great and Large meteorite falls, which were right at the earliest onset of our solar system. And the Earth was no different from the other planets. It was hit as many times as the other planets. But obviously we have weather and atmosphere, and these have served to weather away, erode away most of the evidence of craters on the surface of our planet. And of course, the plate tectonics moving the plates around, as it gets subducted, the evidence will be lost as it gets subducted under the surface. These are four of the probably most famous craters or structures. You'll recognize the one at the bottom because that's the Reese crater, the one in the bottom right. We've already discussed that. You can actually see more clearly here the shape of the crater. And this is an enhanced image from the satellite. Within this, there are about 5 villages that exist between this, and it's a really interesting place to visit because as your train goes through the actual rim of the crater, you can actually, it's physically visible enough to detect when you're going through it. The top right is the Chicxulub, and this is kind of how we found it. It was done by geophysical surveys, by magnetic surveys under the ground, beginning to discern a kind of ring-shaped structure to it, which when closely examined and bored and drilled, we began to find much more evidence of an impact. The bottom left hand is probably the most famous of all craters. It's the Barringer crater in Arizona. It's probably fell around 50,000 years ago. Again, rather like the other ones, there isn't that much left of the original meteor, the original impactor. You can find bits and pieces around it, but not actually in the crater. They tried to drill down and they couldn't really find anything within the actual crater, bottom of the crater. But Arizona being a dry desert country, it's not had the same weathering problems that we would have had in the northern hemisphere. So it survived to this day. And one day I kind of hope to go and actually visit it in person, although people say, oh, don't go there, it's just a tourist trap now. I said, oh, well, maybe I'm a tourist. The bottom, the top right, the top left-hand one is the largest known impact structure. It's the Vredefort crater in South Africa. It's about 300 kilometers across. And it fell around about 2 billion years ago. The diameter of the meteorite was calculated to be between 5 and 10 kilometers across. So it was quite a big hit. And there are many, many others now. As we begin to develop our technology, especially aerial photography and satellite imagery, we're actually beginning to see many, many more that we weren't aware of before, which we're becoming much more aware of now. And I'm going to finish it there, and thank you for listening. And just remember, when you're crossing the road, don't just look right and left, look up the way as well, in case something from heaven falls on top of you. And thank you.